Section 6.2. This is probably the most important section in the book. It's on what's called the standard normal distribution. And I looked, a lot of you have not yet completed this homework assignment for Monday's exam, and this section is on the exam. So I'm hoping that this video will help you when you're trying to complete it. We'll see if it does here. So one of the main ideas that this section tries to get across is a correspondence between area and probability. And we've been studying probability quite a bit, and you've learned about area before. So we'll see what we can do. By the way, why? If I go back to the title slide for a minute, because the standard normal distribution, by the way, what is this? Well, we've been studying distributions. Back in Chapter 5, Section 2, we learned about a probability distribution. When we say normal distribution, what I want you to think of when you hear the word normal is I want you to think of the bell curve. You've heard of that before. You've probably even seen it before. It looks something like this, a bell. By the way, the first line I drew is the x-axis. Okay? And when we draw the bell, in reality, even though people don't always do this, there should be arrowheads on each side. And the x-axis here is an asymptote for the bell curve. There's a word you may remember from algebra. The curve gets closer and closer to the x-axis, but it never actually touches it. And areas under the curve, we're going to be computing areas under the curve. This is going to somehow represent probability. Now why? Well, here's an example. Suppose a satellite crashes at a randomly selected point on the surface of the Earth. What is the probability that it will crash on land? So, in order to compute this, the probability of some event, let me make E be the event that the satellite crashes on land. Well, what I need to do, remember from Chapter 4, is I'm going to have a fraction. The probability of the event occurring is somehow, well, when we did this, we had down here what was called a sample space, right? And up here we had what was called the event. Really what we had was the size of the event over the size of the sample space. And it used to be I would list all the possibilities, and that would be my sample space. So for example, if I was rolling 2 dice and talking about the probability of rolling a certain number with 2 dice, I might list the numbers 2 through 12 here at the bottom, right? Although that doesn't quite work. Anyways, how do I measure size in this situation? Well, the answer is that's the best way to do size here is to think about area. And so what I'm going to do is I'm going to write my fraction using values down here. I want to know the area, well really the surface area of the world. I guess I'll look that up for you here in a second. And up above, well, we're going to want to know the area of land on the Earth. And if I put these in this ratio, that'll somehow give me the probability then of this event, the probability of hitting land. So let me pause and look up those numbers for you. So I got the area of land is 54,225,000 square miles, I think. Let me double check. Yep, square miles. And then I got 142,715,000 square miles for the total surface area of the Earth. And of course, it takes work and geometry to figure those things out, and so I'll just give those to you. That's not the purpose of this course. But if we work out what that equals, On a calculator, I got 0.275. Okay? So the probability that it will crash on land, well, 27.5%. And some of you may have learned before that the Earth is 70 or 75% covered with water. Well, yeah, this shows it, right? So we see there is a correspondence between area and probability. That's really the point of this problem. Now we're going to talk about something called a density curve. See, in this section, when we talk about the normal distribution is our first example of what is called a continuous probability distribution. When you have a continuous probability distribution, say it says continuous, you can have what's called a density curve, and maybe I should say instead of probability histogram. So this is going to be a picture that tells me how the probabilities are distributed, but it's not going to be a histogram. It's a curve. And let's see what the properties are. Well, the first one, the total area under the curve must equal 1. And that's because, well, area under the curve, so say the normal distribution, this represents probability. And because something has to happen, you have to be somewhere under the curve. And so if I were to add up all of the area, the total area under the curve must equal 1. Of course, this is kind of weird because remember I said there's arrowheads on each side? So to really understand what I mean by all the area under the curve, you have to keep going, and this involves limits and calculus, and some of you haven't studied that yet, but that won't prevent us from using the ideas. By the way, back when we did discrete probability distributions and we were talking about histograms, you might remember we had a rule that if you add up the probabilities, that had to equal 1, because something has to happen. So this is the analog of rule number 1. And rule number 2 said every point on the curve must have a vertical height that is 0 or greater. That is, the curve can't be below the x-axis. Notice the bell curve, even if you go way out to the right or to the left, it's always above the x-axis, right? And there was a rule that was like that back in the discrete case, and that was that the probabilities always had to be bigger than 0. And of course, they had to be less than 1, but that's because they all add up to 1. Okay? Now, because the total area under the curve is equal to 1, we have this correspondence. Now, before your book talks about the normal distribution, they decided to give an example of what's called a uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over a range of probabilities. The graph of a uniform distribution results in a rectangular shape. My wife actually, when she goes to work in downtown Cleveland, she takes the rapid transit. She takes the train in. And so she leaves from our house. And every 12 minutes during rush hour, a rapid leaves. And so if she's not paying any attention to the schedule, she just leaves the house. Here's a good question. How long will she have to wait for the rapid? Well, I could have a random variable x here that is the waiting time. And x is a random variable. I want you to notice x is a continuous random variable. She could wait 3 minutes. She could wait 2 minutes. She could definitely wait 2.5 minutes or 2 3/4 minutes, right? X could take on any value in some interval. I told you the rapid by our house comes every 12 minutes. So it could arrive right when she gets there and she doesn't even wait. That would be 0. And I guess the longest she would have to wait would be if it left just when she was getting there. And I've heard this happen many times. And then she'd have to wait a full 12 minutes for another one. So, you know, the value that she'll have to wait is somewhere between 0 and 12. And so I would want to maybe say, well, how long does she have to wait? Well, somewhere between 0 and 12. Maybe she'll wait 6 minutes. Maybe somehow that would be the average time. We'll learn how to compute the mean or the expected value of x at some point here. We already did that for the discrete case. But because it can take on any value, what we do is we're going to draw, well, again, we called it the density curve. And in this case, the density curve is not curved at all. It's straight. Because, why? Because any value, 9 minutes or 10 minutes, these are all equally likely to occur if she doesn't pay any attention to the schedule, if she just leaves the house. This is a classic example of a uniform distribution, the waiting time for a train. By the way, how tall is this rectangle? That's a good question. Well, if we say we're going from 0 to 12 here, so that's the range, then in order to get it so that the total area under the curve is 1, which is what I want, to make this a probability distribution, I guess I would want the height to be very small. I'd make it 1/12. And then 1/12 times 12 is 1. So you'll see this in the examples in the book. This example in the book, they're saying that we have a uniform distribution, and these are voltage levels. Notice the x-axis here is voltage. So it says, let's see if we can find the probability that a randomly selected voltage level is greater than 124.5 volts. So again, let me label a little bit here. X is voltage level. It's a random variable. Voltages could be between 123 and 125 volts. And notice it's continuous, right? Definitely continuous. So that's why 124.5 is a possibility. So what we're trying to compute when we're computing a probability, the probability is represented by the area of, well, this rectangle. Because if we want the voltage to be greater than 124.5, what I'm saying is between 124.5 and 125. Okay? So that's I guess I can get the width of the rectangle. And the width of the rectangle is 0.5. Now I'd like to get the height of the rectangle. Of course, that's labeled over on the side as 0.5. By the way, does this number make sense? In the last example, my height, remember, was 1/12. I guess this is 1/2. Now why is that? Remember, the total area under the curve is supposed to be 1. Does that work when this is 1/2? Yeah, because this is from 123 to 125. The total length is 2. 2 times 1/2 is 1. So how much area is here? Well, 1/4. They work it out. It's 0.5 times 0.5. 1/2 times 1/2 is 1/4. 0.25. Now, what the rest of the chapter is about, and what the really important section of this chapter is about, is the normal distribution. Normal distribution, you need to know something. You need to know the mean, mu, and you need to know the standard deviation, sigma. Okay? Now, for all the problems in this section, section 2, we have what is called a standard normal distribution. The normal distribution always looks like a bell curve. So you have the x-axis and you have the bell curve. When you have the standard normal distribution, I can tell you mu is 0. The mean is 0. And the standard deviation sigma is 1. So let me draw a picture of that. Here's the bell curve. And so right here in the center, that mean, mu, is 0. And when I say the standard deviation is 1, so The title of this slide says Finding Probabilities When Given Z-Scores. We've already studied Z-scores. Remember that a Z-score tells you how many standard deviations you are away from the mean. So if the mean for the normal distribution is 0 and the standard deviation is 1, then I can move over a certain amount, well, to 1. And by the way, 1 on the graph is going to be at the point of inflection of this curve. If you ever studied calculus, you'll know what that means. But it's right about here, halfway down the curve. And that would be 1 standard deviation. And if I move to the left, of course, on the x-axis, that's -1. And that is also 1 standard deviation away. So when we talk about z-scores, I think it's important for you to understand that we're moving along the x-axis. Here is 2. That's 2 standard deviations away from the mean. And here is -2. And remember that 2 standard deviations was significant because we said that if I'm more than 2 standard deviations away, that's unusual. I guess my bell curve graph isn't really good here. It gets asymptotic. That means it gets really close to the x-axis as it moves out. And so while there is some area below the curve to the left or right of -2 or 2 outside that region, there's very little area. Okay. So it says finding probabilities when given z-scores. How do you do it? And there are a lot of different ways you can do it. There's a table in the book, in Appendix A, that can you look up on the edges. You look up the z-score here and here, and then you look in here and you'll see a percentage. And the percentage is the area under the curve. If you decide to use the table, you will see a picture of a normal distribution. Starting here, you'll see is colored in. And if you're on the first table, it goes up to about here. And you'll notice that all the z values are negative. So if it was -0.5, I guess on this graph down here, the z-score would be right there. And you'd be talking about that much area. You'll notice also that as you get closer and closer to 0, the probabilities or the areas get closer and closer to 0.5. And actually, if you look up on the table 0, exactly half of the area is to the left of 0. And of course, half of the area is to the right of 0. So if you have a z-score of something that's positive, then you will have more than 50% of the area. So that's important to understand. And we'll see as we do examples how that works. The formulas and tables insert card is the same information you have in the back of the book or in the appendix. And of course, you're allowed to use that on the exam. There are plenty of other ways that the book talks about. They talk about a program called StatDisk or Microsoft Excel or Minitab. I'm going to show you how to compute these probabilities given z-scores with the calculator, because again, you're allowed to use that on the exam, and it's pretty easy to do. Problem 38, I think, is a very nice problem to do right now, and it says about blank percent of the area, and they mean the area under the standard normal distribution curve, is between z equals -2 and z equals 2. Now when you do these problems from this section, I really think it's a good habit and an important thing to do is to actually draw a sketch of a normal distribution. And it doesn't have to be perfect. And what I want to do is I want to label the mean. So here mu is 0. And so here's 1, and here's 2, and here's -1, and here's -2. These are my z values. And so what I'm trying to do is figure out how much area is between -2 and 2. Now if you're going to use the chart, you're going to have to separate it into pieces. If you were to do the chart, what you would do is you would first look up how much area is to the left of -2. And then you would look up how much area is to the left of 2. And then what you'll do is you'll subtract those values. So let me look that up for you now and get that for you. If I look up on the chart for 2, I would see that 0.9772 is the area to the left of 2. And then I'll subtract the area to the left of -2, which is 0.0228. And so I get 0.95, well, 44, but about 95% of the area. So let's show you how to do that on the graphing calculator. It's a little bit faster. So I take out my graphing calculator, and what I want to do is click on Distributions. And let me show you where that is. Right here, the VARS key, variables, above that in yellow is distributions. So I'll hit Second Distribution. And notice it says normal PDF, normal probability density function, and normal CDF, cumulative density function. This is actually the one I want, normal CDF. And what it'll do is it'll compute the area under a standard normal curve. All you have to do is type in the z-scores that you want to be between. So -2, 2. And if I type that in, there's my 0.9544. I guess if I rounded, it'd be 0.9545. And that's a real nice, quick way to do it. Let's move on to problem 34. In this problem, they're talking about a thermometer, but really what you're doing is you're trying to compute the probability of a z-score being bigger than 3.68. In other words, if I draw the picture, I am really far away from the mean here, because here's 0. Here's 1. Remember, as I move along the x-axis, this is asymptotic. It gets closer and closer to the x-axis without ever touching. By the time you get to 4 standard deviations, it is incredibly close. So 3.68 is right here. We want to know what's the area under the curve as I move to the right of 3.68. And of course it goes on forever, but that doesn't mean there's an infinite amount of area. In fact, you can look it up in the chart. The way to get this would be to look in the chart where it says 3.50 and up. And notice that, well, the picture of the complement of that, right? So that would be all this area, all the way up to 3.68. It says that that area is 0.9999. In other words, very close to all of the area. There's a very tiny amount of area here. And to show you how, so I'm going to demonstrate here, before we do problem 34, an idea. Suppose that I were to compute the area greater than 0. In other words, let's find the probability that a z-score is greater than 0. Well, you can tell from the picture by symmetry that that's going to be exactly half of the area. But I want to show you how to do that on the calculator. So I typed in normal CDF 0, and I put a really big number, 10. See, 10 standard deviations would be off of the screen. So if I press enter, well, notice our calculator gives me 0.49999. If I round, I get 5. Just for kicks, let me up it a little bit. So I went 100 standard deviations away. Well, I guess that's the calculator gives me the same result. It doesn't say 50%. It says, well, about half the time. If you round, you get 50%. Okay. So anyways, if I want to do the probability of z being bigger than 3.68, what I can do is hit normal CDF. And instead of typing 0 here, I can type 3.68 comma, and then you just need to type something big, and 10 is big enough. And if I type in enter, well, what is that? 1.16 e negative 4, that means times 10 to the negative fourth, so you move the decimal place 4 to the left, so that's 0.0001, and then whatever the other digits are, 6, another 1, and then 6, 6. That's incredibly unlikely that we will be that far to the right. Remember when we were talking about unusual? We said things are unusual if they're more than 2 standard deviations away from the mean. Notice that in our last computation, problem 38, we realized that more than 95% of the time, we will be between the standard deviations of -2 and 2. And that's the reason that we decide less than 5%, that's unusual. Now, if you don't think less than 5% is unusual, well then you would have a different range. But this is pretty standard. And we will see that as we move into chapters 7 and 8 also. Okay, one last thing to do. Remember we talked about percentiles, and so I might be curious in the following. How do I represent a percentile with a z-score? See, because when I say the 95th percentile, if I score in the 95th percentile, that means that I am doing better than 95% of the population. So on the picture, if I have a normal distribution, I know that I would be on the right-hand side once I'm above 50%. So I might be curious as to what z-value corresponds to the 95th percentile. And actually, if you look on the chart in the book, on the back of the book, here you're going to try and find, right in the middle of the chart on the right-hand side, where it says 0.9505 is about as close as you can get. Or over here, I guess it says 0.9545, and they put a little asterisk that tells you what the z-value is. But if you want to get that with the calculator, you can click on, again, that distribution. So I'm going to clear this for a minute. Second, variables. And now, instead of typing normal CDF, choice 2, I'm going to type inverse norm, choice 3. And I'll type in the z-value. No, I'm sorry. I will type in the area. So the area I want is 0.95. And what it'll do is spit out the correct z-value. And so the z-value that corresponds to that is 1.645. 1.645 if I round. So we learned how to do a couple of things. We learned how to go from z-scores to probability and area. And that was choice 2 on the calculator, normal CDF. And now we just learned how to go from area, 95% of the area, or the 95th percentile, back to a z-score. And hopefully this will help you as you try the homework. Please draw these sketches when you do the homework, and this is going to help us in the remainder of the course as well. Bye for now, and good luck with the studying. Keep firing the questions.